Okay, let's talk about power. Power is a little bit different from energy, but obviously they are very much related. So when we're talking about power, power is really looking at the rate at which you're using energy, okay? So I can write it sometimes as delta E over delta T. That's how you might write a rate of energy use if the rate of energy use is constant. If we're using calculus, we'll get fancier and say dE dt. But really, when you're thinking about power, thinking about energy is being transformed from one type of energy to another type of energy. And power tells you the rate at which this transformation is taking place, okay? So it's connecting a little bit to energy and time. All right, so once again, if we want our formal definition of what power is, this is the best equation we can give you. Power is equal to the rate at which energy is being transformed as a function of time. We look at the units for energy are the watt. It's named after the person, Watt, who redid the steam engine. And of course, energy per time, energy is kilograms meters squared per second squared over seconds. So if we combine all of these together, we get kilograms meters squared over seconds cubed. It's not really useful thinking it that way. Really, the best way to think of it is, again, energy per unit time. That's really the power, how much energy is being transformed in a given unit of time. All right, so 1 watt. 1 watt represents 1 joule of energy used every second. So if the flow is constant, we can use this equation right here. P is equal to delta E over delta T. So if we want to calculate how much energy a 100-watt light bulb uses, we'd rewrite this and say, oops, undo that. Come on. Okay, let me just clear these out. I don't know why it's doing that. We would say that delta E, the amount of energy, is equal to power times the amount of time, okay? So a 100-watt light bulb every second would use 100 joules, okay? This is an old incandescent light bulb, and we don't like these anymore because basically they would use about 100 joules of energy and only produce maybe 2 or 3 joules of light. Very, very inefficient, okay? Now, in fact, if we think about it, the kilowatt hour actually is a unit of power times time. We have power, which is 1,000 watts. We have time, which is 1 hour. So if we multiply the two together, that's where we get the 3.6 million joules. All right. Okay, let's do another calculation. Let's consider an engine. This engine consumes 8 million joules of work every minute. So 8 million joules, okay? Every 60 seconds. 8 million divided by 60, that is equal to 1.3 times 10 to the 5 watts, okay? 10 to the 5th is 100,000. This is 130,000 watts, okay? Probably more convenient to use a metric prefix, 130 kilowatts. All right, so that engine right there, its power, what's producing that much work, is 130 kilowatts. All right. Now, that's not usually the way that we rate the power output of car engines in this country. We are stuck with our old US customary units. But fortunately, the horsepower and kilowatts are actually pretty close in size, okay? Now, 1 horsepower is 745.7 watts. There's even, believe it or not, a metric horsepower, which is slightly smaller, but generally, when we do our conversion, we say 1 horsepower is 0.746 kilowatts, all right? So horsepower is about 3/4 of a kilowatt. They're not far off. They're pretty close. And the way that this unit was devised was, it wasn't so much that 1 horse could only have a maximum power of 1 horsepower. It was that over an average workday, if you worked a horse, their energy output divided by the total time that they would have to work would come out to be somewhere around a horsepower. So when they used to come out and sell farm equipment, and they'd say, well, this tractor is so many horsepower, they're basically telling the farmer that, if you replace this team of horses with this tractor would be able to do the same as, X amount of horses, whatever its horsepower was. Now, this unit was actually suggested by, oddly enough, the namesake for the SI unit for power, and James Watt. And again, it was a way of relating the work done by a steam engine to the work that could be done by agricultural livestock. So once again, use customary units, relating everything to everything else. 1 horsepower is roughly 746 watts, a little under a kilowatt, okay? Or if you want to use a really bizarre US customary unit, it is 550 foot-pounds every second. Okay. Most small cars usually have a maximum power output of about 100 horsepower, okay? Again, roughly, we do the conversion about 74 kilowatts, okay? That's the maximum mechanical power output during peak performance. You want to compare this to a high-end sports car, the Ferrari 355F, one's engine is about 375 horsepower. The old Dodge Viper, believe it or not, Dodge made a car engine with 450 horsepower. Now, when we say production cars, are sort of lying, because some of these really high-end production cars are actually mostly handmade. Bugatti makes these multi-million-dollar cars. The Koenigsegg 1 is also got a very high price. And why do they want such high powers? This car here, 1361 horsepower, or over a megawatt of mechanical energy. Why would you want something that extreme? Well, this actually comes from the next equation that we're going to talk about. The next equation says that power is equal to force times velocity. And it has this equation has a very profound effect on how the force actually decreases as you go faster and faster. Look at this. You are basically set with a certain amount of power, okay? That depends on the engine that you have in your car. But when you look at the force to propel the car forward, okay, that is going to be equal to the power output of the engine divided by the velocity. Again, the faster you go, okay, the less force you're going to be able to generate. The faster you go, however, the more drag the car is going to have. In fact, the drag goes up by the square of the velocity. So at some point, you will not be able to generate more force than drag on the car, and you won't be able to go any faster. So again, why do we have these ridiculous cars? Well, during a normal commute, you don't really need to go much faster then about 70 miles per hour, even in the most extreme situations. You don't need a lot of horsepower. You don't need a lot of power. But for these extreme cars, where the velocity is much higher and the force of drag is very high, you need a very, very large power to overcome a huge force from the drag and also the diminished force that you have just from going fast. Again, that's why these cars have such ridiculous amounts of horsepower. Here's a NASCAR engine. This has a power output, not quite as large as some of the other cars, but still pretty extreme. For only a 5-liter engine, it's half a megawatt, okay, 750 horsepower. But here's the downside of these engines. Even though it's not much bigger than a typical pickup truck engine in terms of size, this thing has to be rebuilt after every race because of the very extreme compression ratios, high internal pressures that happen within this engine. Also, they use pure ethanol. Okay, let's go to something else. Oh, back to our GE90 turbofan engine. Must figure I'm obsessed with these things. This has, as you might guess, much higher power. This is a 111,000 horsepower. So really putting those other engines to shame. 111,000 horsepower. Or if you want to convert that to megawatts, that's 83 megawatts of power, 83 million watts of mechanical energy. So, obviously, we talked about the 777 and its need to have a tremendous amount of force to do the work to create the kinetic energy to get it going. But it's also got to do this quickly. So it needs a very large amount of power in a short amount of time. All right. So 2 of those big engines, over 160 megawatts of power. Again, we can show where that power, force, and velocity equation came from. We'll start with our original equation for work, okay? If we put it in its differential form, sorry for you non-calculus mathletes out there, it takes this form right here. We know that velocity is dx over dt, so I'm going to substitute that in right here. So looking at this, dx is therefore equal to v times dt, right? Okay, so I'm going to make that substitution in there, and it becomes this right here. Here's our f, our dx dt, and then finally dx dt is just v. We get that power is equal to force times velocity. So, again, what we're doing here is taking this original form right here, putting it over dt is probably an easier way of seeing this. This goes here, this goes here. By definition, this is power. And then we get force times velocity. Okay, it's our Fuel Dragsters. These races are crazy. I don't know what the excitement about this is other than pure speed, because they are just racing to go as fast as they can in a short amount of time. These engines are insane. They basically produce an incredible amount of power, but they can only operate for a short period of time because the amount of excess heat that they produce will actually melt the engine if it's kept on too long. So 10,000 horsepower, about 7.5 megawatts for only a brief amount of time is the maximum power for these top drag fuel racers. So again, here's our equation. Power equals force times velocity. So our force is power divided by velocity. At their peak power, traveling at their peak speed, they generate 52,000 newtons of force to push them forward against the drag force of the air. Oh, Boeing 747, very sad. They're starting to retire these. You'll only see them as cargo planes in not too long in the not too long in the future. These jets use, I believe they use the GE next gen engines. All four engines together, they're smaller than the GE 90s, by the way, produce a total net power of 140 megawatts. You only need 90 megawatts for takeoff, and that's a good thing, because if you do the math here, that puts, you take half of 140, that's 70. Half of 70 is 35. If you think about this, each engine's 35 horsepower, right? You have 140 horsepower here. You subtract off 35 if one engine goes out. And what you realize is these things can take off with only 3 engines instead of all 4 engines going. So pretty impressive, pretty impressive. But in any case, this is the Gen NX engine. I forget which one it is, but this is what they use on the 747. And if you think about it, the power output, again, is 200, oops, undo that. Oops. Power output, 284 kilonewtons when it's stationary. But here's the interesting thing. Again, as you go faster and faster, for a given, I'm sorry, the power output we listed before was 140 megawatts with all the engines going. But you know, you look at this, and as we reach a takeoff speed of 80 meters per second, the force actually drops off, okay, for the same amount of power, for 34 megawatts of power per engine at, once again, 80 meters per second. Your force output drops from 284 to only 42 kilonewtons. Here's the granddaddy of them all. This is the most powerful structure ever built to convert energy. This is the Three Gorges Dam. And unfortunately, there were some construction problems with it. This is built in China, and the government of China is running into some real problems with the current flood season. And parts of the spillway are starting to break apart. And while this dam will probably not totally collapse, it's certainly experiencing quite a bit of damage. And it's going to need some extensive repairs so it doesn't fail. But in any case, it generates 22.5 gigawatts of power at full capacity. That's 22,500 megawatts, or 2.25 times 10 to the 10 watts of power. Again, this is the most powerful thing ever built by humans. Okay, let's talk about an important concept related to energy and to power. It is the idea of efficiency. And the way efficiency works is Efficiency, which we use a small e, is basically how much useful energy, the energy that we want, that we get out compared to the energy that we put in. So if we look at this little flow diagram right here, we see for the amount of energy that we put in any system, only a fraction of that will be useful and some of it will be waste. Usually it's lost as heat. Okay, so we're talking about the efficiency of an energy system or a power system. We're looking at the ratio of how much useful we get out compared to how much we put in. Now, for many energy systems, most of the energy is lost in the form of heat. Fluorescent lights are favored over older incandescent bulbs, and they have 4% of the efficiency, which means we get 4 times more useful energy out for the same energy in. However, fluorescent bulbs have a problem. The problem is called mercury. When the fluorescent bulbs break, the mercury is released. This mercury is a very bad heavy metal toxin. So we've been trying to get away from these fluorescent bulbs because invariably they break, the mercury goes into the environment, and it makes it into our food chain where it's very dangerous for us. So instead of using these fluorescent bulbs, we've been replacing them with LED lights. They have higher efficiencies and last even longer than the fluorescent bulbs. And that's what most light bulbs are made out of. Other efficiencies, generators, about 70 to 99% of the energy that goes into them becomes electricity. About 50 to 93% of the electrical energy going into motors becomes mechanical work. Let's look at automobiles in terms of efficiency. Most automobiles are 20 to 30% efficient, which means take all the energy from the gasoline, okay, all the energy you start out with, the chemical energy. That's turned into heat. Some of that energy is turned into work, but most of that heat goes out into the environment. Okay. What we're looking at right here is that most of the energy that goes into the system simply leaves as heat. Okay? So in looking at things, probably anywhere from about 3 to 4 times the amount of energy that we use in these cars is actually simply lost and wasted to the environment. And that's why we're trying to get away from these internal combustion engines. Their thermodynamic efficiencies, as we'll see in physics 2, are really limited by their internal temperatures. Okay? If you operate them any hotter, they become more efficient, but they break down faster. You operate them too cold, they'll last longer, but they'll take more energy and waste more fuel. So what we've been trying to do is use other technologies to improve efficiency. One idea is this idea of a hybrid engine. It combines an internal combustion engine with a generator. Okay? And the idea is this, okay? We operate the internal combustion engine at its peak efficiency, okay? So it is producing the most amount of work it can for the given amount of fuel that is being consumed. When it is on, it is powering this generator, and that is putting energy into a bunch of batteries. Just imagine those are batteries. Not a very good way of doing this, okay? So the internal combustion engine, the generator, really never do anything in terms of directly powering the car itself. They're just there to take this big array of batteries and charge them up. Okay. We then have the motor, okay, which is going to drive it's a little electric motor. It's going to drive the wheels and make the car go forward. Okay. Now, when we want the car to go, we take energy from the batteries and we transfer it into the electric motor. When we want the car to stop, we take the energy from the motor, it becomes a generator, that transfers it back to the battery. Now, in an internal combustion engine, we don't have this ability. In most cases, if we want to slow down, we need to step on our brakes. Our brakes use a non-conservative force. They're just going to turn the energy into heat, and it's going to be lost in the environment. Here, this is regenerative. We can take the energy that we've already put into motion and store it back into the batteries. So this system is much more efficient than a typical car engine because, one, it's operated at the engine's peak efficiency, okay? It's not left to idle or waste energy at some low RPM or high RPM. It's always operating at its peak efficiency. Next, by using batteries and using an electric motor, we can recoup some of the mechanical energy and store it to be used later on. Diesel engines are a little bit better as far as internal combustion engines are concerned. They're more expensive to make because they have much larger compression ratios. And they also tend, especially with the older diesels, to pollute more. But diesel engines, at least in their more modern form, are a better alternative to internal combustion gasoline engines. Let's compare. Here are all electric vehicles, or EVs. Okay? I'm a little biased, but we'll leave that aside right here. Okay. What's the best we can do with an internal combustion engine? Well, this group right here represents our internal combustion engines. And we see, of all of them, Toyota Corolla does pretty well. It takes 1 gallon of gas to travel 31 miles. That's normally how we rate cars. We rate them according to miles. Oops, and do that. Miles per gallon, MPG. All right. Some cars are better. Nissan Rogue, I don't even know what that is. Okay. Some cars are worse. F-150 pickup. Jeep Wrangler, 18 miles per gallon. All right. So right there you can see these are fairly inefficient vehicles. And really, in terms of their overall efficiency, for the amount of energy that we put in, we don't get very much energy out. All right. Hybrids are a bit of an improvement over that, okay? 52 miles per gallon, 41 miles per gallon. Problem is, they are powered by an IC, an internal combustion engine. So in terms of their efficiency, we can push them pretty close to the 40s and 50s miles per gallon, but that's about as good as we're going to get. Now we compare them to the all-electric vehicles. Okay, look at this one here. Yes, they're more expensive. Tesla Model 3, Tesla Model X, 93 to 130 miles per gallon equivalent. What they're doing here is they're saying, okay, yeah, they don't use gasoline. We know that. But equivalent in terms of how the energy is produced, the equivalent miles per gallon is, oh gosh, why do I keep doing that? Miles per gallon. I'm multitasking. Miles per gallon. The equivalent miles per gallon. What we need to produce that electricity, all right, for the fossil fuels that we burn to put the energy on the grid, that car will travel much farther, okay? Over 100 miles per gallon, okay? I think earlier I even showed you how much energy the batteries can store. And there's the Chevy Bolt right there, 119. There's the Nissan Leaf, 112. And even though some of these cars only go 250 miles per charge, they're using maybe an equivalent about two gallons of gas compared to what another car would do to do that same distance. Let's say like the Toyota RAV4 right here. It would use to go that 250 miles 5 times as much energy. Your body also has different efficiencies. You have 2 different muscle types. One type of muscle has about a 27% efficiency, which means that when you burn the fuel, 27% of that goes into work. 73% becomes nothing more than heat. Your type 2 muscles are much worse than that, 13%, which means 87% of the energy is simply turned into heat. Okay? It's just the way our bodies are. We can't really improve on those efficiencies much more than that. What this shows you is when you work out aerobically, okay, your efficiency is about twice as high as when you work out anaerobically. So the energy that is used by the muscles when you're going for a jog and you're using as much oxygen as you're taking in is double what it is if you sprint. You ever notice after you sprint, you're breathing really hard? You're trying to catch up for that oxygen deficit because there was no way for your lungs to bring in the oxygen required to power your muscles while you're at a full sprint. Here are the different efficiencies, or different powers for the different muscle types. And again, distance fibers, these are slow twitch type 1, are very low power. They contract very slowly. Type 2X are the most powerful but least efficient. And type 2A sort of sits somewhere in between. Let's go back to light bulbs. Incandescent light bulbs. For the most part, the government worked to phase out incandescent bulbs because they were very inefficient. Okay? Once again, why? 95% of the energy that went into them, in the best case scenario, sometimes it was even worse, was basically turned into nothing more than heat. Okay? So basically, an incandescent bulb is a much better heater than it is a light. Okay? 95% plus of the energy becomes heat. Only about 3 to 5% becomes useful energy we see it we use to see. So again, a push was made to get rid of the incandescent bulbs and go to other technologies. Now, halogen lamps are technically incandescent bulbs, but they're not really doing all that much better. Yes, they boost the efficiency by about 40%, but that still only puts you up about 7%. When I mean a 40% boost, I mean over the 5%. You're getting 2% more. Okay? And what these bulbs do is they pass electricity through a tungsten filament at a higher temperature, but by using halogen gas, the filament doesn't burn out as quickly. Fluorescent bulbs, anywhere from 4 to 5 times better in terms of efficiency than are incandescent bulbs. Again, the big problem that that we had with these bulbs for a while is we certainly got much better efficiencies, but it came at a cost. The mercury vapor inside these bulbs, which are used to create the UV light, which is then converted to visible light, is highly toxic. So fluorescent bulbs do better in terms of our carbon footprint, but in terms of the introduction to heavy metals into the environment, which naturally happens just by accidentally breaking these bulbs, was a steep price to pay. Eventually, we've been able to switch to a new technology, which has been around for quite some time, and these are light-emitting diodes. The idea of a light-emitting diode is that we pass electricity through a semiconducting material, we call it diode, okay? Di means two. And the way that we create these diodes is we take some type of semiconducting material, one which is doped with positive impurities, okay? We call these p-type. Another end that's doped with n-type. And if we sandwich them together and then send electricity through them, at their gap where they join together, they give off light, okay? And they're very, very efficient. The problem is, when these LEDs first came on the market, they first came on the market producing infrared light, okay? That wouldn't have been very useful for us to use. They gradually improved, and eventually they got red and some other colors, green, yellow. But the one color they always had some difficulty with was blue, okay? Now, not the same semiconductors that you get in computer chips. These are a little bit different. And I don't know if you can really see this, but the original red up to yellow semiconductors were gallium aluminum arsenic. Then they went to gallium arsenic phosphide. And you say, oh my God, they're using arsenic. It's so little, it's really not of any consequence. But you can create different proportions of this and produce colors from red to yellow. And there's also aluminum, gallium, indium phosphide. God, it's been a while since I had my chemistry. Then they went to gallium phosphide and gallium nitride to make green. But again, the shorter wavelengths just weren't available. It wasn't until we got to the shorter wavelengths that we had the potential to produce what are called white LEDs. And in fact, the people who invented these blue and violet LEDs using indium gallium nitride won the Nobel Prize because it was such an important discovery. Okay, in any case, how do you get a white LED? Well, you need a blue or a violet LED to do this. And the reason for this is the blue light, okay, blue light leaving this, all right, can interact with a phosphorescent material, okay? It's actually cerium, yttrium, aluminum garnet. It's the cerium ions inside the yttrium, aluminum garnet, or YAG, that gives these different colors. But as a blue light goes through, it can be converted into shorter wavelengths, such as green. It's called yellow phosphor because it looks yellow. It actually produces green light, yellow light, and some longer wavelengths, red. And that is all colors of the spectrum. And basically, what that allows us to do is turn the blue light from the diode itself using this phosphor material into white light. Okay, this is actually exactly what the fluorescent bulbs did. The fluorescent bulbs themselves actually generated UV light. They didn't directly create the white light that we see from them. They would create UV light, and then it hit the phosphorus material on the sides. Again, you're usually like a cerium oxide or some other combination, and that would produce the white light. So basically, these blue LEDs were replacing the functionality of the mercury vapor, except for they weren't toxic. And instead of having this big fluorescent bulb, we had these tiny, they're only about the grain, size of about the grain of sand, some of them, these tiny little LEDs that would produce all colors of light. And that's had a tremendous impact on the lighting industry. The prices have come down. They're extremely efficient. And again, if you actually did a color spectrum of one of these, what you would see is the blue LED. The blue LED was producing light, as its name implies, in the blue end of the spectrum. Okay, also somewhat into the violet part of the spectrum. So you have blue and violet light right here coming from this. And then the cerium ions in the yellow phosphor would give you the green light, the yellow light. I don't even think I'm doing anything here. And the red light. So although you wouldn't get a perfect representation of what sunlight would be like, it was a pretty good, it's pretty close. Wasn't too bad. Like if I were to do the actual spectrum of sunlight, it might look something more like this. Okay, so some of these LEDs have sort of a bluish edge to them. And what they'll do is to make them warmer, they'll actually add in addition to yellow phosphor, they'll add some red phosphor here. This makes them less efficient, but it gives them a warmer glow, more like the incandescent bulbs. So again, advances in LED technology have made them more efficient, but they've also made them more powerful than they have been in the past. So LEDs were oftentimes used for indicator lights in electronic equipment. Now they become bright enough where they can be a primary source of light. And again, comparing light sources, here is the basic cost. Again, if you were to go out and buy an incandescent bulb, they would be very, very inexpensive to purchase. Say an old 60-watt incandescent bulb. In terms of the brightness, we measure brightness in what are called lumens. Puts out about 800 lumens. But the cost would come from two things. One, they don't last very long. 75 hours keeping them on, the tungsten filament would fail on average, is not all that long. Okay. You think about it, what is that, about a month? If they're on 24 hours, you think 24 hours times 30 days, it gets you around 750 hours. Also, because you use a lot of electricity to produce 800 lumens, the operating cost would come mostly from the electricity that you'd use. Now, we compare that to an LED, all right? For the same amount of light, you're still producing 800 lumens of light, same exact amount. You're only using 9 watts. So the overall cost is one fraction of what you are using in terms of electricity. And these things would last for 25,000 hours. So, many, many times longer than the incandescent bulbs. The initial cost could be much greater when you bought them, but over the entire lifetime of the bulb, you would end up saving for what would be probably a bulb for a few dollars, $162.